It is now time to discuss the normal and tangential coordinate system for the kinetics of a particle. Now remember from chapter 12, we use the normal and tangential coordinates whenever we're dealing with a curvilinear motion and information about the path is given. Now this information could be the radius of curvature, for instance. So let us develop the second law equation in terms of normal and tangential components. So we start off again with sigma f equals to ma. Now looking at the figure on the right, we know that we need to split both vectors in terms of the three different axes with unit vectors ut, un, and ub. So the left hand side would be equal to sigma ft ut plus sigma fn un plus sigma fb ub. And that's equal to m times at ut plus an un plus ab ub. Now again, similarly to what we have done in the rectangular components, we can split the different components we have, so ut, un, and ub, and write three different equations. So the first equation is sigma ft equals to mat, the second equation is sigma fn equals to man, and finally, whenever you're dealing with a motion that occurs on a single plane, the third component will always have zero acceleration, so one can write that sigma fb is equal to 0. So those are the three equations one has when working in the normal and tangential coordinate system. Now, what is the methodology to solve problems for that coordinate system? Well, the steps or the method is exactly the same. First, you need to select a coordinate system. In that case, we're dealing with the normal and tangential components. Next, we need to draw the free body diagram, which is the left-hand side of the equation. We need to draw the kinetic diagram, assuming specific sign conventions if the acceleration is unknown, as we have said before. And finally, identify the different unknowns and solve for the variable we're looking for. Now, as I have said before, sometimes you might need to make use of the kinematic equations, but in the case of the normal and tangential coordinates, most of the time you will actually make use of the kinematic equations, and that's because we have standard equations for the acceleration in the normal axis and acceleration in the tangential axis. And the equations, if you remember, are an equals to v squared over rho, and at is equal to dv over dt. And these two equations are actually very useful since they help us get rid of two unknowns in the three equations of motion we have here. So by simply calculating these based on the information we're given in the problem, one can get rid of the unknowns from the right-hand side and actually look for unknowns from the left-hand side.